You are thinking right now. Electrical signals are racing through your brain at hundreds of miles per hour, forming patterns, making connections, building meaning out of raw sensation. This ability, this thing we call intelligence, feels like the most powerful force in the universe. We split the atom, we decoded our own DNA, we sent machines to the edge of the solar system. And somewhere deep in the back of your mind, you assume this will continue. You assume that intelligence, once it exists, finds a way to survive, that it spreads, adapts, and endures. But physics disagrees. The same laws that allowed your brain to evolve, the same thermodynamic gradients that power every thought you have ever had, are disappearing. Slowly, irreversibly, and with absolute mathematical certainty, the universe is not just indifferent to intelligence. It is actively dismantling the conditions that make intelligence possible. And the most terrifying part is not how it ends. It is that there may be nothing, no technology, no cleverness, no cosmic trick that can stop it. Let us begin with a statement that sounds obvious but carries devastating implications once you follow it to its conclusion. Thinking costs energy, not metaphorically, not in some poetic, hand-wavy sense. Literally, every single thought you have ever had required a measurable quantity of fuel to produce. Your brain accounts for roughly 2% of your body mass, but it consumes approximately 20% of your total energy budget. Right now, as you process these words, glucose molecules are being ripped apart inside your neurons. Oxygen is being consumed, heat is being released, waste products are being flushed into your bloodstream. Your brain is a furnace. It never stops burning. If you cut off its fuel supply for even a few minutes, consciousness collapses. Neurons begin to die. The lights go out. This is not a design flaw. This is a fundamental requirement. Intelligence, in any form we have ever observed or theorized, is a physical process. It requires matter arranged in specific configurations. It requires energy flowing through that matter. And it requires a difference, a gradient, between hot and cold, between order and disorder, between concentrated energy and dispersed energy. Without that gradient, nothing happens. No signals fire. No information gets processed. No thoughts form. The gradient is the lifeblood of every mind that has ever existed. Now, most people hear this and shrug. Of course, thinking takes energy. So does running. So does digestion. Everything biological costs something. But here is where it gets dangerous. Here is where the implications start to bite. The energy your brain uses does not come from nowhere. It comes from food. The food comes from plants and animals. The plants get their energy from the sun. The sun gets its energy from nuclear fusion, converting hydrogen into helium at a rate of roughly 600 million metric tons of hydrogen every single second. And the sun got its hydrogen from a cloud of gas that collapsed under gravity billions of years ago. That gas was forged in the first few minutes after the Big Bang, when the universe was hot enough to fuse protons and neutrons into light elements. Follow the chain far enough and you arrive at a single, uncomfortable realization. Every thought you have ever had is powered by the original energy budget of the universe. There is no external source. There is no cosmic gas station where the universe pulls in for a refill. The total energy was set at the beginning, roughly 13.8 billion years ago, and it has been redistributing itself ever since. It has not increased. It will not increase. The tank was filled once, and we have been running on it ever since. But the problem is not that the energy is disappearing. Energy is conserved. The first law of thermodynamics guarantees that the total energy in a closed system remains constant. You cannot create it. You cannot destroy it. You can only move it around. So if the total energy never changes, why should we worry? Because energy has a quality, not just a quantity, and that quality is degrading. Imagine a waterfall. The water at the top has potential energy. It is high up. It can fall. As it crashes down, that potential energy converts into kinetic energy, into sound, into heat, into the erosion of rock. By the time the water reaches the pool at the bottom, it has lost its height. It is still water. It still has the same mass, the same number of molecules, but it can no longer power a watermill. It can no longer do useful work without being lifted back up. The energy has not vanished. It has spread out. It has gone from a concentrated, useful form to a dispersed, useless form. This is the essence of the second law of thermodynamics, and it is the single most important law in all of physics for understanding the fate of intelligence. The second law says that in any isolated system, entropy, which is a measure of disorder, of energy dispersal, of the number of microscopic arrangements that look the same from the outside, tends to increase over time. It does not say entropy must increase in every single interaction. It says that statistically, overwhelmingly, irreversibly, entropy increases. The universe moves from order to disorder, from concentration to dilution, from difference to sameness, from the waterfall to the still pool. This is not a suggestion. It is not a guideline. It is the most experimentally verified principle in all of science. No exception has ever been observed. Not once, not in any laboratory, not in any corner of the cosmos, not in any epoch of cosmic history. The arrow of entropy points one way, and it never reverses. Now, here is the connection that most people miss. Intelligence is an entropy machine, not in the sense that intelligence creates disorder, though it does. In the sense that intelligence requires disorder to be created. Every computation, every thought, every act of information processing works by taking energy from a concentrated source and dispersing it. Your brain takes glucose, a structured molecule full of chemical potential energy, and breaks it down into carbon dioxide and water, molecules with far less usable energy. The difference, the gradient between the structured fuel and the degraded waste, is what powers the electrical signals in your neurons. Without that gradient, your neurons are just wet tissue. They cannot fire, they cannot think, they cannot be aware. This means that intelligence does not just use energy, it uses energy differences. And the second law of thermodynamics is systematically, relentlessly destroying every energy difference in the universe. Every star that burns is converting nuclear potential energy into light and heat, spreading it across the void. Every planet that radiates warmth into space is smoothing out a temperature gradient. Every chemical reaction that runs to completion is flattening a potential energy hill. The universe is ironing itself out. It is becoming uniform. And when it becomes fully uniform, when every region of space is at the same temperature, when every gradient has been leveled, when the cosmic waterfall has reached the bottom, there will be nothing left to power a thought. This is not a distant, abstract concern. This is the trajectory we are on right now. Let us make this even more concrete. Let us talk about what it actually costs to think at the most fundamental level. In 1961, a physicist named Rolf Landauer, working at IBM, proved something that sounds almost absurd in its precision. He showed that there is a minimum energy cost associated with erasing a single bit of information, not a practical cost, not an engineering limitation, a fundamental thermodynamic cost set by the laws of physics themselves. The principle is now called Landauer's principle, and it states that erasing one bit of information in a computation at a given temperature must dissipate at least kT times the natural logarithm of 2 in energy, where K is Boltzmann's constant and T is the temperature of the environment. At room temperature, this works out to roughly 3 times 10 to the power of minus 21 joules per bit erased. That is a fantastically small number. It is trillions of times less than the energy your laptop currently wastes per operation. Modern computers are nowhere near this limit. They burn millions of times more energy per operation than Landauer's minimum because they are engineered for speed, not thermodynamic perfection. So you might think this limit is irrelevant. You might think it is just a theoretical curiosity. But that is exactly the wrong conclusion. Because Landauer's principle is not about today. It is about the end game. It is about the most efficient computer that could ever be built by any civilization, anywhere in the universe, at any point in cosmic history. Even a civilization a billion years more advanced than us, with technology so sophisticated it looks like magic, cannot beat this limit. It is baked into the structure of thermodynamics. It is a wall that no amount of engineering genius can climb over, and what this means is devastating. It means that computation, the physical process underlying all intelligence, all thought, all awareness, is fundamentally and inescapably tied to entropy production. You cannot think without paying the tax. Every bit of information processed, every logical operation performed, every memory stored or retrieved adds a tiny but non-zero amount of entropy to the universe. Thinking heats the cosmos, and you cannot avoid it. Now, multiply this across the scale of a civilization. Imagine a species that has mastered its entire galaxy. It has built computers around every star. It has harnessed every available energy source. It is processing information at a rate that dwarfs anything we can currently comprehend. Even this civilization, at the peak of its power, is bound by Landauer. Every computation it runs, every thought it thinks, every simulation it generates, pushes the universe slightly closer to thermal equilibrium. The very act of being intelligent accelerates the erasure of the conditions that make intelligence possible. It is a cruel paradox. The smarter you are, the faster you consume the gradients you depend on. The more efficiently you think, the more slowly you consume them, but you still consume them. There is no equilibrium state where intelligence persists without cost. You are always spending, you are always drawing down the account. And the account is finite. Let us zoom out even further and look at this from the perspective of the universe as a whole. The cosmos began in a state of extraordinarily low entropy. This is one of the deepest and most puzzling facts in all of physics. At the moment of the Big Bang, the universe was hot, dense, and almost perfectly uniform. That uniformity, paradoxically, represents a state of extremely low gravitational entropy. Gravity is a clumping force. It wants matter to collapse into dense concentrations, into stars, into black holes. A smooth, uniform distribution of matter is, gravitationally speaking, like a perfectly ordered deck of cards. It is far from the most probable arrangement. It is special, it is unlikely, and it contains an immense reservoir of potential. The potential for matter to clump, for stars to ignite, for temperature gradients to form, for chemistry to happen, for life to emerge. The entire history of the universe, from the first hydrogen clouds to the formation of galaxies, to the ignition of stars, to the synthesis of heavy elements, to the assembly of planets, to the emergence of self-replicating molecules, to the evolution of brains, all of it has been powered by the slow, grinding, irreversible unwinding of that initial low entropy state. We are living off the original endowment. Every structure in the universe, every galaxy, every ecosystem, every neural network in every brain exists because entropy has not yet finished rising. We are in the middle of the great dispersal. The waterfall is still falling. The gradient still exists, but it is getting smaller. And when that happens, and physics says it will happen, the game is over. Not just for us, for all intelligence, everywhere. This is the part that requires you to adjust your sense of scale. We are not talking about threats that operate on human timescales, centuries, or millennia. We are not talking about the kind of danger you can prepare for with a bunker or a space colony. We are talking about a process that is woven into the fabric of reality itself. entropy increase is not an external enemy. It is the operating principle of the cosmos. It is the reason anything happens at all. Chemical reactions proceed because they increase entropy. Stars shine because fusion increases entropy. Your brain functions because metabolism increases entropy. Intelligence rides the wave of entropy production like a surfer on a breaking wave. The wave is magnificent. It is powerful. It carries us forward. But waves break. They always break. And when this wave finishes breaking, when the entropy of the universe approaches its maximum value, when the last gradient has been smoothed out and the last temperature difference has been erased, there will be nothing left to ride. The surfer does not get to stay on the board forever. The ocean will become perfectly flat, and on a flat ocean, nothing moves. You might be tempted to look for an escape hatch. You might think that surely, with enough technology, a sufficiently advanced civilization could find a way around this. Maybe they could create new gradients. Maybe they could reverse entropy locally. And indeed, this is exactly what living organisms do. Life is a local entropy reversal machine. You take disordered raw materials, food, water, air, and assemble them into the staggeringly ordered structure of a living body. Your cells build proteins with nanometer precision. Your DNA stores information with a fidelity that puts our best hard drives to shame. Life decreases entropy locally. But here is the catch that the second law never lets you forget. Every local decrease in entropy is paid for by a larger increase in entropy somewhere else. Your body stays ordered by pumping disorder into the environment. You breathe in oxygen and breathe out carbon dioxide. You eat structured food and excrete degraded waste. You radiate heat into the surrounding air. The total entropy of the system, you plus your environment, always goes up. Always. You can rearrange the furniture in one room, but only by making a bigger mess in the hallway. And the hallway is the universe, and the universe has no hallway of its own. There is no outside. There is no dumpster to put the cosmic waste into. The entropy stays, it accumulates, and it never, ever goes back down. This is the fundamental reason why intelligence may not be a permanent feature of the cosmos. It is not because of bad luck. It is not because of a hostile alien species. It is not because of a catastrophic asteroid or a rogue black hole. It is because the very process that powers thought, the conversion of low-entropy energy into high-entropy waste, is a one-way street, and the road has a finite length. We do not know exactly how long the road is. We do not know exactly when the last usable gradient will be exhausted. But we know, with the certainty of tested physical law, that it will be exhausted. The second law does not negotiate. It does not make exceptions for species that are clever or brave or desperate. It simply runs. It runs in every star, in every cell, in every circuit, in every thought. It runs right now, inside your head, as you process the meaning of this sentence. You are paying the entropy tax at this very moment. And the receipt is non-refundable. So here is where we stand. Intelligence is not a gift from the universe. It is a loan. It is a temporary arrangement made possible by a specific set of thermodynamic conditions, conditions that were established at the Big Bang and have been deteriorating ever since. Your brain is a heat engine that runs on chemical gradients. A computer is a heat engine that runs on electrical gradients. A hypothetical alien megastructure harvesting the energy of a star is a heat engine that runs on gravitational and nuclear gradients. Every form of intelligence ever conceived, biological, digital, quantum, exotic, is a heat engine, and all heat engines obey the same iron law. They require a difference between hot and cold, between order and disorder, between usable energy and waste. When that difference reaches zero, the engine stops. No exceptions, no appeals, no clever tricks. The engine stops. The universe gave us this gift of difference, this precious gradient, this thermodynamic slope that our minds can tumble down and call it thinking. But the slope is not infinite. It has a bottom, and we are sliding toward it. Everything that follows in this story, the death of stars, the evaporation of black holes, the expansion of space, the isolation of galaxies, the freezing of the cosmic background, all of it is the machinery by which the universe flattens the slope. All of it is the mechanism by which the conditions for intelligence are steadily, permanently erased. We are going to trace that mechanism across the entire future of the cosmos. We are going to watch the lights go out, one by one, and ask at each stage whether intelligence can adapt, migrate, or transform itself fast enough to survive. And we are going to confront the possibility that the answer at every stage is no. Not because intelligence is weak, but because physics is patient and entropy always wins. We have established that intelligence is a thermodynamic process. It runs on gradients. It feeds on difference. It requires concentrated energy flowing toward dispersal, and it rides that flow the way a turbine rides a river. But knowing that intelligence needs fuel is only half the story. The other half is understanding what happens to the fuel supply. And to understand that, we need to look at the future of the universe, not the next century, not the next millennium. We need to look at timescales so vast that the entire history of human civilization, from the first campfire to the last satellite, compresses into a single pixel on the timeline. We need to follow the cosmos from where it is now, through its slow decline, into its final state. And what we find at the end of that journey is not an explosion, it is not a dramatic collapse, it is something far worse. It is silence, absolute, permanent, thermodynamic silence, a state in which nothing can happen, nothing can change, and nothing can think ever again. Right now, in cosmological terms, we are living in paradise. Astronomers call this epoch the stelliferous era, the age of stars. It began a few 100 million years after the Big Bang, when the first hydrogen clouds collapsed under gravity and ignited nuclear fusion. It will last, by most estimates, for roughly another 100 trillion years. That sounds like an unimaginable amount of time, and it is. 100 trillion years is so long that the current age of the universe, 13.8 billion years, represents barely more than 1/100th of 1% of the stelliferous era's total duration. We are in the opening seconds of the age of starlight. And yet, even this paradise has an expiration date. Stars are not eternal. They are nuclear reactors with finite fuel reserves. A star like our Sun has been steadily fusing its hydrogen supply for 4.5 billion years and has enough left to continue for roughly another 5 billion. It has been doing this for about 4.5 billion years, and it has enough hydrogen left to continue for another 5 billion or so. When the hydrogen in its core runs out, the Sun will swell into a red giant, shed its outer layers, and collapse into a white dwarf, a dense, fading ember roughly the size of the Earth. It will glow faintly for trillions of years, cooling asymptotically toward the temperature of the surrounding space, but it will never ignite again. Its nuclear fuel is spent. Larger stars burn faster and die more spectacularly. A star 10 times the mass of the Sun exhausts its fuel in mere tens of millions of years, ending in a supernova that scatters heavy elements across space and leaves behind either a neutron star or a black hole. The most massive stars live the shortest lives. They burn with ferocious intensity and die young. But the smallest stars, the red dwarfs, are the misers of the cosmos. A red dwarf with 1/10 of the Sun's mass burns its hydrogen so slowly that it can shine for trillions of years. These tiny, dim furnaces will be the last stars standing, long after our Sun has become a cold cinder, long after the great blue giants have all exploded and faded. The red dwarfs will still be glowing, faintly, weakly, but persistently. They will be the last campfires in a darkening universe, but even they will eventually run out of fuel. Roughly 100 trillion years from now, give or take, the last red dwarf will exhaust its hydrogen, contract, cool, and go dark, and when it does, the stelliferous era will be over. No new stars will form because the raw material, the cold hydrogen gas that collapses into stellar nurseries, will have been used up or dispersed beyond recovery. The age of starlight will end, and it will never return. What comes next is called the degenerate era, and it is a universe you would barely recognize. The cosmos will be filled with the corpses of stars, white dwarfs, neutron stars, and black holes. These objects still contain energy, but it is locked away in forms that are increasingly difficult to access. White dwarfs are essentially giant crystals of carbon and oxygen, glowing with residual heat. Over timescales measured in quadrillions of years, they will radiate that heat into space and cool to the background temperature of the universe. They will become black dwarfs, invisible, inert spheres of degenerate matter drifting through the void. Neutron stars will follow a similar trajectory, cooling and dimming until they are indistinguishable from the darkness around them. The galaxies themselves will dissolve. Gravitational interactions between stars, even dead ones, will gradually eject most objects into intergalactic space over timescales of roughly 10 to the power of 19 to 10 to the power of 20 years. The majestic spiral arms, the dense galactic cores, the vast halos of dark matter, all of it will slowly unbind. Stars will be flung into the void like sparks from a dying fire. The remaining cores of galaxies will be dominated by their central, supermassive black holes, which will gradually consume whatever debris drifts close enough to fall in. But even this process is not eternal. Eventually, there will be nothing left to consume. The black holes will sit alone in the expanding darkness, surrounded by nothing. And then, even the black holes will die. This is one of the most remarkable predictions in all of theoretical physics. In 1974, Stephen Hawking showed that black holes are not truly black. They emit radiation, an agonizingly faint glow of particles produced by quantum effects near the event horizon. This is called Hawking radiation, and it carries energy away from the black hole. Because the radiation removes energy, the black hole slowly loses mass. It evaporates. The process is absurdly slow. A black hole with the mass of our sun would take roughly 10 to the power of 67 years to fully evaporate. A supermassive black hole, the kind that sits at the center of a galaxy, might take 10 to the power of 100 years or more. These are numbers so large that they make the age of the current universe look like less than a rounding error. But they are finite. And finite means they end. One by one, over time scales that stretch the meaning of the word patience, every black hole in the universe will evaporate into a faint mist of photons and elementary particles. When the last black hole evaporates, the universe enters its final chapter. Physicists call it the dark era, and it is, in every meaningful sense, the end. The dark era is not a dramatic apocalypse. It is the opposite of drama. It is a universe in which nothing happens. The cosmos will be filled with a thin, cooling gas of photons, neutrinos, and perhaps a scattering of electrons and positrons. These particles will be spread so thin and moving so slowly that interactions between them become vanishingly rare. The temperature of the universe will approach, but never quite reach, absolute zero. And crucially, there will be no gradients left, no pockets of concentrated energy, no temperature differences between one region of space and another, no chemical potential waiting to be released. The cosmic waterfall will have reached the bottom. The pool will be perfectly still, perfectly uniform, perfectly dead. This state is called thermodynamic equilibrium, and it is the final destination of the second law. It is the state of maximum entropy, the state toward which the entire universe has been drifting since the moment of its birth. And in this state, computation is impossible. Not difficult, not expensive. Impossible. Because computation requires energy gradients, and there are none left. There is no hot reservoir to draw power from. There is no cold reservoir to dump waste heat into. Every point in space is at the same temperature as every other point. And in a system at uniform temperature, no work can be extracted. This is not a technological limitation. It is a theorem. It is a consequence of the Carnot efficiency limit, which states that the maximum amount of useful work you can extract from a heat engine depends on the temperature difference between its hot and cold reservoirs. When that difference is zero, the efficiency is zero. No work, no computation, no thought. Now, you might be wondering whether any clever physicist has tried to find a loophole. The answer is yes, and the most famous attempt came from one of the great minds of the 20th century. In 1979, the physicist Freeman Dyson published a paper titled Time Without End: Physics and Biology in an Open Universe. It is one of the most creative and optimistic papers in the history of cosmology. Dyson asked a simple question. If the universe is going to get colder and colder, can intelligence survive by simply slowing down? His argument was elegant. Imagine a civilization that can reduce its metabolic rate, its rate of thinking, its rate of computation, in proportion to the declining temperature of the universe. As the cosmos cools, the civilization thinks more slowly. It stretches its computations over longer and longer intervals. A single thought that once took a second now takes a year, then a millennium, then a billion years. But from the subjective perspective of the intelligence, time passes normally. It does not feel slow. It feels the same as it always did, because its internal clock has slowed down in perfect proportion to the external temperature. Dyson showed that if the universe is open, meaning it expands forever but does not accelerate, then a sufficiently clever civilization could, in principle, perform an infinite number of computations over infinite time. It would have to hibernate between thoughts, shutting down entirely, and then waking up to think for brief intervals, dumping waste heat into the ever colder background. But the math worked. The total energy required could remain finite even as the total number of thoughts approached infinity. It was a beautiful result. It was a lifeline. It said that intelligence could persist forever, not by fighting the heat death, but by gracefully adapting to it. For 20 years, Dyson's paper was the great hope. It was the answer to the despair of the second law. Yes, the stars will die. Yes, the black holes will evaporate, but intelligence, patient, slow, adaptable intelligence, could outlast them all. It could ride the cooling curve all the way down, thinking fewer and fewer thoughts per unit of external time, but never stopping entirely. It was the cosmic version of Zeno's paradox, always approaching the end but never quite arriving. And then, in 1998, the universe pulled the rug out. Two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying distant supernovae. They were trying to measure the rate at which the expansion of the universe was slowing down. Everyone expected it to be slowing down. Gravity pulls matter together, so the mutual gravitational attraction of all the galaxies in the universe should be acting as a brake on the expansion, gradually decelerating it over time. The question was simply how fast the braking was occurring. But the data said something nobody anticipated. The expansion was not slowing down, it was speeding up. The universe was accelerating. Distant supernovae were dimmer than expected, meaning they were farther away than expected, meaning the expansion had been picking up speed for billions of years. This discovery, which earned all three scientists the Nobel Prize in 2011, implied the existence of a mysterious repulsive energy woven into the fabric of space itself. We call it dark energy, and despite decades of study, we still do not know what it is. What we do know is what it does. It pushes. It causes space to expand at an ever-increasing rate. And it does not dilute. Unlike matter and radiation, which thin out as the universe expands, dark energy maintains a roughly constant density per unit volume of space. This means that as space grows, the total amount of dark energy grows with it, driving the expansion faster and faster in a runaway feedback loop. This discovery destroyed Dyson's loophole. Here is why. Dyson's scheme required the universe to cool asymptotically towards zero, but never quite reach it. It required the background temperature to keep dropping, always providing a slightly colder reservoir for waste heat. But in an accelerating universe dominated by dark energy, the situation is fundamentally different. The acceleration creates a cosmological event horizon, a boundary beyond which light can never reach you. This horizon has a temperature. It is called the de Sitter temperature, named after the Dutch physicist Willem de Sitter, and it is set by the energy density of the dark energy. It is fantastically low, roughly 10 to the power of minus 30 degrees above absolute zero. But it is not zero. And this is the critical point. In a universe with a cosmological constant, the background temperature never reaches zero. It floors out at the de Sitter temperature. The universe approaches a state of thermal equilibrium at this temperature and stays there forever. This means that Dyson's strategy of thinking slower and slower in proportion to the declining temperature hits a wall. The temperature stops declining. It plateaus, and once it plateaus, there is no colder reservoir to dump waste heat into. The Carnot efficiency drops to zero. Computation becomes thermodynamically impossible. The civilization cannot slow down any further because there is no further to go. It is as if Dyson's cosmic Zeno's paradox was running beautifully, with the tortoise forever approaching the finish line, and then someone built a concrete wall 50 meters before the end. The tortoise hits the wall. Game over. The implications are staggering. In a universe dominated by dark energy with a positive cosmological constant, there is a hard upper limit on the total number of computations that can ever be performed. Not a practical limit, a fundamental, physics-imposed ceiling. No matter how efficient your computers are, no matter how cleverly you manage your energy, no matter how slowly you think, there is a finite number of thoughts available, and when they are used up, intelligence stops permanently. This is not like running out of gasoline, where you can switch to another fuel. This is like running out of thermodynamic possibility. There is no alternative fuel, because the fuel, in the deepest sense, is the temperature gradient between your processor and the environment, and that gradient has been reduced to zero by the relentless expansion of space. Some physicists have tried to quantify this limit. The calculations depend on assumptions about the cosmological constant and the available matter energy within a causal horizon, but the estimates all point in the same direction. The number is finite, spectacularly large, but finite. And for the question we are asking, the question of whether intelligence can last forever, the difference between a very large number and infinity is the difference between a long life and immortality. And the universe has chosen the long life. It has denied us immortality. Let us sit with what this means. The heat death of the universe is not merely the death of stars. It is not merely the evaporation of black holes. It is not merely the cooling of matter to near absolute zero. It is the death of computation. It is the end of information processing. It is the permanent, irrevocable cessation of all possible thought. In the dark era, the universe will still exist. Space will still be there, particles will still drift, photons will still travel, but nothing will happen. Nothing can happen, because happening requires difference, and difference has been eradicated. There will be no observers to notice the silence, because observers require computation, and computation requires gradients, and gradients no longer exist. The universe will persist in a state of maximum entropy for a duration that makes all previous cosmic epochs look like the first frame of a movie. It will sit there, uniform and featureless, for timescales so long that mathematicians have to invent new notations to write them down. 10 to the power of 10 to the power of 100 years. Longer, perhaps forever, if the cosmological constant persists. And throughout all of that time, not a single thought will be thought. Not a single calculation will be performed. Not a single bit of information will be processed. The universe will be, in the deepest and most literal sense, mindless. This is the endpoint that the second law has been driving towards since the beginning. The initial low entropy state of the Big Bang was like a wound-up clock. The Stelliferous era, the age in which we live, is the clock unwinding. The gears are turning. The hands are moving. Interesting things are happening. Stars shine. Planets form. Molecules self-organize. Brains evolve. Civilizations rise. But the spring is losing tension. The clock is running down. And when it stops, it does not restart. There is no hand to wind it again. The second law ensures that the clock moves in only one direction, from wound to unwound, from ordered to disordered, from alive to dead. We are living inside the ticking. We are the ticking, and the ticking will stop. There is something uniquely disturbing about this form of cosmic death. Other apocalyptic scenarios, a vacuum decay event, a big rip, a big crunch, are violent. They are sudden. They are dramatic. There is a strange comfort in a dramatic death because it implies that something happened, that the universe went out with a bang. The heat death offers no such comfort. It is not an event. It is an absence. It is the universe not going out at all, but simply fading, cooling, spreading thinner and thinner until the concept of an event becomes meaningless. It is a death by dilution, a death by patience, a death so slow that no individual moment feels like the end. Yet the cumulative result is total and permanent cessation. Imagine falling asleep so gradually that you never notice the transition from waking to dreaming to nothingness. That is the heat death. The universe does not scream, it yawns. And then it is gone. And here is the detail that makes physicists most uncomfortable. This is not just one possible future among many. Given what we currently know about the cosmological constant, given the observed acceleration of the expansion, given the measured energy density of dark energy, this is the most likely future. It is the default ending. It is what happens if nothing unexpected intervenes. No phase transition saves us. No new physics rescues us. The equations, our best equations, the ones that have been tested and confirmed by decades of precision cosmology, point here. They point to a universe that is spending its thermodynamic inheritance with no way to earn more. They point to a cosmos that will eventually become a featureless, uniform, computationally barren void. They point to the extinction not just of life, not just of intelligence, but of the very possibility of intelligence. And yet, perhaps you are not ready to give up. Perhaps you are thinking that the universe is vast, that it contains resources we have not yet imagined. That somewhere out there, in the geometry of space-time or the structure of quantum fields, there is an energy source or a computational trick that could keep thought alive past the heat death. It is a natural impulse. It is, in many ways, a noble one. And in the next stage of this story, we are going to examine that impulse carefully. We are going to look at the geometry of the expanding universe, at the horizons it creates, at the prisons it builds around every observer, and we are going to ask whether even the cleverest civilization, with access to every resource within its reach, could squeeze enough computation out of the cosmos to think forever. The answer, as you may have guessed, is no. But the reasons why are not just about energy, they are about space itself, about the structure of the cosmos, about the walls that the expansion builds between every island of matter. The universe is not just running out of fuel, it is locking the remaining fuel behind doors that no one can open. We have watched the stars burn out. We have followed the universe into thermodynamic equilibrium, a state where no gradients remain and no computation can occur. We have seen Dyson's beautiful loophole, the idea that intelligence could survive by thinking slower and slower, crushed by the discovery that the expansion of the universe is accelerating. But all of that was about energy, about fuel, about the supply side of the ledger. Now we need to talk about something different. Something that, in many ways, is even more suffocating. We need to talk about space itself. Because the expanding universe is not just draining the fuel tank, it is building walls, invisible, absolute, inescapable walls that are sealing off regions of the cosmos from one another permanently. Even if you had unlimited energy, even if you somehow found a way to cheat the second law, the geometry of the universe would still imprison you. The expansion is not just a backdrop to the story of cosmic decline. It is an active participant. It is the architect of the loneliest prison ever constructed. A prison with no bars, no locks, and no guards, just distance, growing faster than anything can cross it. And every thinking being in the universe is already inside. To understand this prison, we need to understand what a cosmological event horizon is. And to understand that, we first need to be clear about what the expansion of the universe actually means. Most people picture the expansion as galaxies flying apart through space, like shrapnel from an explosion. But that is not what is happening. The galaxies are not moving through space. Space itself is expanding. The distance between galaxies is increasing because new space is being created between them. Imagine drawing two dots on a rubber band and then stretching the band. The dots did not move along the band itself grew. The dots are farther apart, not because they walked away from each other, but because the surface they are sitting on expanded beneath them. This distinction matters because it means there is no speed limit on how fast two objects can recede from each other. Special relativity says that nothing can travel through space faster than light. But it says nothing about space itself stretching. The expansion of the metric, the fabric of space-time, is not constrained by the speed of light. And in a universe with accelerating expansion, this has a terrifying consequence. Beyond a certain distance, space is expanding so fast that light emitted from a distant galaxy will never reach us. Not because the light is slow, not because something is blocking it, but because the space between us and that galaxy is growing faster than the light can cross it. The photon is running on a treadmill that is speeding up. It will run forever and never arrive. The distance at which this happens defines our cosmological event horizon. It is a sphere centered on us, and beyond its edge, no signal, no particle, no information of any kind can ever reach us. Anything beyond that horizon is gone, not temporarily, not in the sense of being far away and hard to reach, gone in the sense of being causally disconnected from us for all eternity. We will never see it, we will never interact with it, we will never know what happens to it. It might as well not exist. And here is the part that tightens the noose. The horizon is shrinking. Not in the sense that the sphere is getting smaller in absolute terms, but in the sense that more and more objects are crossing it. The accelerating expansion is pushing galaxies beyond the horizon faster than new light from them can arrive. Right now, the observable universe contains roughly 2 trillion galaxies, but we are already losing them. Galaxies at the edge of the observable universe are receding from us at speeds exceeding the speed of light. Their light, emitted today, will never reach us. They have already crossed our event horizon. And as the expansion continues to accelerate, driven by dark energy, more and more galaxies will follow. The Andromeda Galaxy, our nearest large neighbor, is gravitationally bound to the Milky Way, so it will remain accessible. The galaxies of the local group, a small cluster of more than 80 known galaxies held together by mutual gravity, will eventually merge into a single large elliptical galaxy over the next few 100 billion years. But everything beyond the local group is on its way out. The Virga cluster, the Coma cluster, the great superclusters that stretch across hundreds of millions of light years, all of them are being carried away by the expansion. One by one, they will redshift into invisibility, their light stretched to wavelengths longer than the observable universe, and then they will cross the horizon entirely. In roughly 100 billion years, give or take, an observer in what used to be the Milky Way will look out at the sky and see nothing. No distant galaxies, no cosmic web, no large-scale structure of any kind. Just the merged remnant of the local group, a single aging galaxy floating in an apparently empty universe. The night sky will be black, not because the stars are far away, but because everything else has been erased from the visible cosmos by the expansion of space. Now, think about what this means for a civilization trying to survive. We established earlier that intelligence requires energy, and that energy is finite. A natural strategy, perhaps the only rational strategy for a sufficiently advanced civilization, would be to expand, to reach out across the cosmos, colonize new star systems, harvest new energy sources, and build a network of computational infrastructure spanning as much of the universe as possible. More territory means more resources. More resources means more computation. More computation means more time for intelligence to persist. This is the logic behind every serious proposal for long-term survival. Spread out, grab everything you can, build an empire of thought that stretches across the galaxy, across the supercluster, across the observable universe. But the expansion is working against you, and it is working relentlessly. Even if a civilization began expanding at close to the speed of light the moment it achieved the technology, it would still be racing against a horizon that is pulling away faster than it can chase. There is a maximum volume of space that any civilization can ever access. No matter how early it starts, no matter how fast it travels, this volume is determined by the cosmological parameters of the universe, primarily the density of dark energy and the current rate of expansion. Physicists call the boundary of this accessible region the cosmic event horizon, and the total volume of spacetime that any single observer can ever causally influence or be influenced by is called the causal diamond. The causal diamond is the intersection of your future light cone, everything you could ever send a signal to, and your past light cone, everything that could ever send a signal to you. It is the totality of your causal reach. Everything outside it is as inaccessible to you as a parallel universe. And in a cosmos dominated by dark energy, the causal diamond has a finite volume. A hard, non-negotiable, physics-imposed finite volume. This means that even in the best-case scenario, even if a civilization is perfectly efficient, perfectly aggressive, perfectly strategic in its expansion, it can only ever access a limited amount of matter and energy. The rest of the universe, the overwhelming majority of the universe, is beyond the wall. It is expanding away too fast to ever be reached. The resources that exist out there, the stars, the hydrogen clouds, the raw materials for computation, are as useless to you as resources in a universe you cannot enter. You might as well be staring at a photograph of food. It cannot nourish you. This is not a technology problem. This is a geometry problem. The walls are not made of steel or force fields. They are made of expanding space-time, and no engine, no warp drive, no amount of ingenuity can outrun the expansion of space itself, because the expansion is not motion through space, it is the growth of space. You cannot fly faster than the ground beneath you is stretching. So, the civilization is trapped inside its causal diamond. It has a finite volume of space-time to work with. The question then becomes, how much computation can you squeeze out of that finite volume? Is it enough to sustain intelligence indefinitely, or is there an upper bound? The answer comes from two of the deepest results in theoretical physics, the Bekenstein bound and the holographic principle, and both of them deliver the same verdict. There is a ceiling, and it is absolute. The Bekenstein bound, proposed by Jacob Bekenstein in 1981, places a maximum on the amount of information, measured in bits, that can be contained within a given region of space with a given amount of energy. The formula is precise. The maximum number of bits is proportional to the product of the energy and the radius of the region divided by a constant involving Planck's constant and the speed of light. What this means, in plain terms, is that even if you could somehow arrange every single particle in your causal diamond into the densest possible information-storing configuration, you would still have a finite number of bits to work with. You cannot store infinite information in a finite region, and if you try to pack too much information into too small a space, you do not get a denser computer. You get a black hole. The universe has a built-in firewall against infinite information density, and that firewall is gravitational collapse. Push past the Bekenstein limit, and space-time itself intervenes, swallowing your computer into a singularity. The holographic principle takes this idea even further. Proposed by Gerard Hooft and developed by Leonard Susskind, the holographic principle states that the maximum amount of information that can be contained within any volume of space is not proportional to the volume. It is proportional to the surface area of the boundary enclosing that volume. This is deeply counterintuitive. We naturally expect that if you double the size of a room, you double the amount of stuff you can put in it. But the holographic principle says that the information capacity of a region scales with the area of its walls, not the volume of its interior. The implication is that the three-dimensional world we inhabit has the information density of a two-dimensional surface. It means that the total computational capacity of any region of space-time, no matter how vast, is fundamentally limited by the area of its boundary. Applied to the causal diamond of an observer in a dark energy-dominated universe, this gives a finite, calculable upper bound on the total number of bits that can ever be processed. The numbers vary depending on the exact cosmological model, but they converge on estimates in the range of 10 to the power of 120 to 10 to the power of 122 operations. That is the ceiling. Every calculation, every simulation, every moment of awareness that any civilization within our causal horizon will ever produce must fit beneath it. The number is staggering, but it has an edge, and an edge is all the second law needs. Now, you might be thinking about alternative energy sources. What about black holes? Cannot a civilization harvest energy from black holes long after the stars are gone? The answer is yes, in principle. And in fact, black holes are spectacularly efficient energy sources. The Penrose process, proposed by Roger Penrose in 1969, shows that it is possible to extract rotational energy from a spinning black hole. You send matter into the ergosphere, the region just outside the event horizon where space-time is dragged along by the black hole's rotation. Under the right conditions, the matter can split, with one fragment falling into the black hole and the other escaping with more energy than it came in with. The energy comes from the black hole's spin. In theory, you can extract up to 29% of a black hole's total mass energy this way. That is an extraordinary amount. A stellar mass black hole contains more energy than our sun will produce in its entire lifetime. A supermassive black hole contains more energy than an entire galaxy of stars. And the process does not require any exotic physics. It is classical general relativity. A sufficiently advanced civilization could build structures around black holes, sometimes imagined as devices that dangle matter into the ergosphere and harvest energy for trillions upon trillions of years. But there are limits. Once the rotational energy is extracted, the black hole settles into a non-rotating state, a Schwarzschild black hole. At that point, the Penrose process stops working. The only remaining energy source is the Hawking radiation. And Hawking radiation is, for all practical purposes, useless as a power source for most of the black hole's lifetime. The reason is temperature. The temperature of a black hole is inversely proportional to its mass. A solar mass black hole has a temperature of roughly 60 billionths of a degree above absolute zero. That is colder than the cosmic microwave background radiation, which currently sits at about 2.7 degrees above absolute zero. A black hole that is colder than its environment does not radiate. It absorbs. It gains energy from the surrounding radiation faster than it loses energy through Hawking radiation. Only when the cosmic background cools below the black hole's temperature will the black hole begin to evaporate and release net energy. For a solar mass black hole, this will not happen for an almost inconceivable stretch of time. The black hole simply sits there, inert, waiting for the universe to cool around it. And when it finally does begin to evaporate, the power output is minuscule. A solar mass black hole emits Hawking radiation at a power of roughly 10 to the power of minus 29 watts. That is less than the energy carried by a single photon of visible light per year. You cannot run a civilization on that. You cannot run a calculator on that. You would have to wait for the black hole to shrink, which increases its temperature and its radiation rate. But the overwhelming majority of the energy is released in the final instance of evaporation in a burst that lasts a fraction of a second. The energy is available, but it comes all at once, at the very end, after an almost endless wait. Harvesting black holes is not a strategy for eternal computation. It is a strategy for extending computation by a finite amount across a staggering but ultimately bounded timescale. What about the cosmic microwave background itself? The CMB is a bath of photons left over from the Big Bang, filling all of space with a faint glow at a temperature of roughly 2.7 Kelvin. As the universe expands, this radiation cools. Could a civilization use the CMB as a low-temperature heat source and dump waste heat into an even colder reservoir? In principle, yes, as long as a colder reservoir exists. But the de Sitter temperature flaw we encountered earlier destroys this strategy too. The CMB will eventually cool below the de Sitter value, at which point the horizon radiation becomes the dominant background, and that background is everywhere. It surrounds you uniformly, with no cold spot to dump waste heat into. The same thermodynamic wall that killed Dyson's hibernation strategy kills this one. The CMB is a useful energy gradient today, but it has an expiration date set by the cosmological constant. What about vacuum energy? Could a civilization tap into the energy of empty space, the quantum fluctuations that seethe beneath the surface of the vacuum? This idea has a powerful appeal because vacuum energy is everywhere. It pervades all of space. In fact, dark energy itself may be a manifestation of vacuum energy. If you could extract even a tiny fraction of it, you would have access to a virtually unlimited power source. But the physics is unforgiving. The vacuum state is, by definition, the lowest energy state of the quantum fields. You cannot extract energy from the ground state of a system because there is no lower state to transition to. It would be like trying to dig a hole at the bottom of the ocean. There is nowhere to put the water. Proposals for extracting vacuum energy typically rely on the Casimir effect, the measurable force between closely spaced conducting plates caused by the difference in vacuum fluctuations inside and outside the gap. And it is true that the Casimir effect demonstrates that vacuum energy is real. But extracting net usable energy from the Casimir effect requires you to do work to bring the plates together, and the energy you get back is exactly equal to the work you put in. There is no free lunch. The vacuum does not give up its energy without a compensating cost. Every serious analysis of vacuum energy extraction has concluded the same thing. The vacuum is a floor, not a reservoir. You can stand on it, but you cannot mine it. So let us tally the score. Stars will die. That eliminates nuclear fusion as a long-term energy source. Black holes will evaporate. That provides an enormous but finite reservoir of energy that takes almost incomprehensibly long to access and delivers most of its payload in a single terminal burst. The cosmic microwave background will cool to the de Sitter temperature and plateau. That eliminates it as a usable gradient. Vacuum energy cannot be extracted because the vacuum is already the ground state. And the expansion of space is locking resources behind event horizons faster than any civilization can claim them. Every door has been closed, every window has been sealed. The causal diamond is a box, and inside that box, the total number of computations is finite. The civilization can be as clever as it wants. It can optimize its algorithms. It can reduce its energy consumption to within a whisper of the Landauer limit. It can slow its thinking to a crawl. It can hibernate for eons between thoughts. But the total number of thoughts is bounded. The box has a capacity, and that capacity is set by the geometry of space-time and the thermodynamic properties of the vacuum. When the capacity is reached, thinking stops. Not because the civilization made a mistake, not because it was not smart enough, but because the universe has a finite computational budget, and the budget has been spent. This is the geometry of despair. It is not enough to say that the universe is running out of energy. The universe is also running out of room. The expansion is isolating every island of matter from every other island. The galaxies that we can see today will, one by one, slide beyond our horizon and vanish. The merged remnant of the local group will sit alone in an ocean of expanding emptiness, slowly exhausting its finite reserves with no possibility of reinforcement. Any signal we send into the void will redshift into meaninglessness. Any probe we launch will eventually cross the horizon and be lost. We are not just running down a battery. We are running down a battery while the walls of our room shrink around us and the doors lock one by one. The universe is not merely dying, it is compartmentalizing its death, ensuring that every civilization, no matter how far it spreads, eventually finds itself alone in a sealed chamber with a finite air supply. And there is a bitter irony here. The very force that is killing us is the same force that made us possible. The expansion of the universe is what cooled the primordial plasma enough for atoms to form. It is what created the density fluctuations that collapsed into galaxies and stars. It is what gave us the thermodynamic gradients, the temperature differences between hot stellar cores and cold interstellar voids that power all chemistry, all biology, all thought. The expansion built the playground, and now it is dismantling it. The same mechanism that spread the pieces across the board, giving us a rich and structured cosmos to explore, is now sweeping the pieces off the edge, one by one, until the board is empty. We were born from the expansion, and we will die from the expansion. The universe giveth, and the universe taketh away, and it taketh with compound interest. So where does this leave us? We know that intelligence requires energy gradients. We know that all gradients are being erased by entropy. We know that the accelerating expansion creates a hard boundary on the resources any civilization can access. We know that the total computation within that boundary is finite. We know that no known energy source, not stars, not black holes, not the vacuum, escapes these constraints. The physical universe, the stage on which intelligence performs, is being systematically stripped of every property that makes performance possible. But perhaps you are still not ready to surrender. Perhaps you are thinking about the medium of intelligence itself, Maybe the universe cannot provide infinite energy, but what about the hardware? What about the minds themselves? Could biological intelligence evolve to survive these conditions? Could artificial intelligence, running on substrates we have not yet imagined, push past the boundaries that flesh and blood cannot cross? It is a reasonable hope. It is perhaps the last reasonable hope, and that is what we need to examine now. The fragility of biological intelligence, the promise and limits of post-biological minds, and whether changing the thinker can save thought itself from the dying of the light. We have spent this journey so far building a case against the universe. We have shown that energy gradients are finite and disappearing. We have shown that the expansion of space is locking resources behind impenetrable horizons. We have shown that the total computational budget of the cosmos is bounded by the geometry of space-time itself. The verdict seems final. Intelligence cannot last forever because the physical conditions that support it are temporary. But throughout all of that analysis, we treated intelligence as an abstract process. We talked about computation, about bits, about Carnot efficiency. We never looked at the computer itself. We never asked what intelligence is made of and whether the material matters, because there is a stubborn, deeply human hope buried in this question. The hope that even if the universe is dying, maybe the mind can adapt. Maybe it can change its body, shed its skin, upgrade its hardware. Maybe biological intelligence is just the first draft, a prototype scratched out by evolution on a wet, fragile, temporary planet. And maybe the final version, the one that actually has a chance against the heat death, is something else entirely. Something made of silicon, or diamond, or plasma, or exotic matter we have not yet discovered. Something that does not need oxygen, or water, or a narrow temperature band to survive. Something that can think in the cold, in the vacuum, in the dark. This is the hope of post-biological intelligence, and it is worth examining carefully, because if it fails, if even the most advanced conceivable mind cannot escape the constraints we have described, then the case is truly closed. Intelligence is not just endangered. It is temporary by design. Let us start with what we know. Biological intelligence, the only kind we have ever observed, is spectacularly fragile. Your brain is a 3-pound lump of fatty tissue suspended in cerebrospinal fluid inside a bone shell. It operates within a temperature range of roughly 35 to 41 degrees Celsius. A few degrees above that range and proteins begin to denature. Enzymes stop functioning. Neural signaling becomes erratic. You hallucinate, seize, and die. A few degrees below, and metabolic processes slow to the point where consciousness fades into coma. Your brain requires a constant supply of oxygen. Cut it off for 4 minutes, and neurons begin to suffer irreversible damage. Cut it off for 10, and the architecture of your mind is destroyed beyond recovery. It requires glucose delivered through a network of blood vessels so fine that a single clot the size of a grain of sand can obliterate your ability to speak, move, or recognize your own family. It is vulnerable to radiation, to toxins, to mechanical shock, to a staggering catalog of parasites, pathogens, and prion diseases. It degrades with age as proteins misfold, telomeres shorten, and the cellular repair machinery gradually loses its battle against entropy. The human brain is, by any engineering standard, a marvel of computational density. It packs roughly 86 billion neurons, each connected to thousands of others, into a volume slightly larger than a cantaloupe. It processes sensory information, generates motor commands, stores decades of memories, and produces the subjective experience of consciousness, all on about 20 watts of power, less than a dim light bulb. No artificial system comes close to this efficiency, but the brain's brilliance is inseparable from its fragility. It is a machine optimized for one specific environment, the surface of a rocky planet with liquid water, a breathable atmosphere, a stable magnetic field, and a gentle yellow star. Remove any one of those conditions and the machine breaks. Now zoom out from the individual brain to the civilization that produces it. Human civilization, the collective infrastructure of intelligence on Earth, is built on a foundation of ecological and geological stability that is, in cosmic terms, astonishingly precarious. We depend on a planet with a molten iron core that generates a magnetic field strong enough to deflect solar wind and cosmic radiation. Without that field, our atmosphere would be stripped away over geological time, as happened to Mars. We depend on a star that has remained stable for billions of years, neither flaring violently enough to sterilize the surface, nor dimming enough to freeze the oceans. We depend on a planetary orbit that stays within the habitable zone, the narrow band of distances where water remains liquid. We depend on the gravitational influence of a large moon that stabilizes our axial tilt, preventing wild climate swings. We may benefit from the gravitational influence of a Jupiter-sized planet in the outer solar system, whose complex interactions with comets and asteroids have shaped the impact history of the inner planets in ways we are still working to understand. We depend on plate tectonics to recycle carbon and regulate atmospheric composition over hundreds of millions of years. Remove any one of these and intelligent life as we know it either never evolves or does not survive long enough to become technological. And even with all of these protections in place, biological civilizations face a gauntlet of existential threats that have nothing to do with thermodynamics or cosmology. Asteroid impacts capable of triggering mass extinctions occur on timescales of roughly 50 to 100 million years. Supervolcanic eruptions capable of inducing global volcanic winters occur on timescales of hundreds of thousands of years. Gamma-ray bursts from nearby stellar explosions could sterilize the surface of a planet with essentially no warning. And then there are the self-inflicted threats: nuclear war, engineered pandemics, runaway artificial intelligence, ecological collapse, any one of which could end a technological civilization before it ever leaves its home planet. This is the landscape in which the Great Filter hypothesis operates. The economist Robin Hanson proposed that somewhere along the path from dead chemistry to star-spanning civilization, there is a step so improbable, so difficult, so lethal that almost no species survives it. If the filter is behind us, perhaps in the origin of life or the evolution of complex cells, then we are the rare survivors, and the galaxy's silence is simply because few species make it to where we are. But if the filter is ahead of us, if technological civilizations reliably destroy themselves or are destroyed before they can expand into space, then the silence means something much darker. It means that intelligence, even when it arises, does not persist. It is a spark that ignites and then extinguishes over and over across billions of worlds, never catching fire long enough to spread. The fragility of biological intelligence is not just a practical inconvenience. It is a structural feature of the medium. Biology runs on chemistry. Chemistry requires specific temperatures, specific solvents, specific molecular interactions that only work under narrow conditions. Life as we know it is a wet, warm, delicate process. It is fantastically creative, capable of generating the extraordinary complexity of a human brain from nothing but atoms and selection pressure. But it is not robust. It is not durable. It is not designed to operate in the environments that dominate the cosmos, the vacuum, the radiation, the extreme cold, the extreme heat, the crushing gravity. 99.9% of the universe is instantly lethal to every biological organism that has ever existed. We are confined to a thin film of habitability on the surface of a small rock, and even that film is temporary. The sun will eventually expand and render the Earth uninhabitable. Biology got us here. But biology cannot take us much further, and certainly not far enough to outrun the death of the stars. This is where the dream of post-biological intelligence enters the picture. The idea is straightforward. If biological brains are too fragile, too slow, too energy hungry, and too dependent on specific environmental conditions, then the solution is to migrate intelligence to a different substrate, build artificial minds, transfer consciousness, or at least the computational processes that generate it, from neurons to silicon chips, or quantum processors, or photonic circuits, or some material we have not yet invented. Freed from the constraints of biology, these minds could operate in environments that would kill any organic creature. They could function in the vacuum of space, where there is no atmosphere to maintain. They could tolerate radiation levels that would shred DNA. They could operate at temperatures far below the freezing point of water, where biological chemistry halts, but solid-state electronics can still function, in some cases even more efficiently. They could slow their processing to match the declining energy budget of the universe, stretching their thoughts across millennia or millions of years, entering a deep computational hibernation between bursts of activity. They could be modular, replacing degraded components, copying their software to new hardware, distributing their processing across multiple nodes for redundancy. In principle, post-biological intelligence solves every problem that makes biological intelligence so vulnerable. And there is a specific physical advantage that makes this dream compelling. The thermodynamic efficiency of computation in a cold environment is actually better than in a warm one. Remember Landauer's principle. The minimum energy cost of erasing one bit of information is proportional to the temperature of the environment. Lower the temperature, and the cost per operation drops. A computer operating at 3 Kelvin, the current temperature of the cosmic microwave background, requires roughly 100 times less energy per bit erasure than a computer operating at room temperature. As the universe cools, computation gets cheaper per operation. This means that a civilization that transitions to machine intelligence and allows itself to cool along with the cosmos could stretch its finite energy reserves across far more computations than any warm biological brain ever could. This is, in a sense, a refined version of Dyson's slowing down strategy. You do not just think slower, you also think more efficiently, because each thought costs less energy in a colder universe. The total number of thoughts you can afford with a given energy budget increases as the temperature drops. But there is a wall at the end of this road, and we have already encountered it. The temperature floor set by the cosmological constant means that each computation always costs something, no matter how far into the future you push it. The Landauer cost per bit never reaches zero. So post-biological intelligence can be more efficient than biological intelligence. Vastly more efficient. Trillions of times more efficient. But each thought still carries a non-zero price tag. And in a universe with a finite energy supply and a minimum charge per operation, the total number of thoughts you can afford is still bounded. Post-biological intelligence extends the window enormously, but it does not open it permanently. The prison is larger, more comfortable, better managed, but it is still a prison, and the sentence is still finite. Let us look at the other promises of machine intelligence and see how they hold up against physics. Durability. Machines do not age the way biological organisms do. They do not suffer from telomere shortening or protein misfolding or immune system decline, but they are not immune to degradation. Every physical substrate degrades over sufficient timescales. Silicon chips are vulnerable to cosmic ray impacts that flip bits and corrupt data. Metal components corrode. Crystal structures develop defects. Solder joints fatigue. And on truly long timescales measured in tens of powers of years, even the protons and neutrons that make up the hardware may not be stable. The standard model of particle physics does not definitively predict proton decay, but many grand unified theories do, with half-lives estimated in the range of 10 to the power of 34 to 10 to the power of 41 years. If protons decay, then every material object in the universe, every computer, every storage medium, Every structural support will eventually crumble into a mist of leptons and photons. You cannot build a computer that lasts forever if the atoms it is made of have an expiration date. You can replace components, of course. You can mine new materials and fabricate new parts. But this requires energy, and energy is finite, and it requires raw materials, and raw materials are finite and increasingly locked behind event horizons. Maintenance is not free. And in a universe where every resource is dwindling, maintenance becomes an ever larger fraction of the budget until it consumes the budget entirely. Redundancy. Distributing intelligence across multiple nodes is a powerful strategy against local failures. If one processor dies, the others carry on. But redundancy only works if the nodes can communicate. And in an expanding universe, communication between distant nodes becomes increasingly difficult and eventually impossible. Signals sent between nodes redshift as space expands. The energy required to send a detectable signal across a growing distance increases without bound. Eventually, the nodes drift beyond each other's event horizons and lose contact permanently. The distributed mind fragments. The network dissolves. Each node becomes an island, alone with its local resources, unable to coordinate, unable to share, unable to think collectively. Redundancy, which was supposed to be the ultimate survival strategy, becomes isolation. The very expansion that threatens the energy supply also dismantles the infrastructure of distributed thought. Substrate independence. This is perhaps the most philosophically seductive idea in the post-biological toolkit. The claim is that intelligence is not tied to any particular material. It is a pattern, a process, a computation that can be implemented on any suitable substrate. If your silicon chips decay, transfer the computation to diamond lattices. If diamond degrades, move to nuclear isomer storage. If matter itself becomes unreliable, encode information in the configurations of photons or gravitational waves. The idea is that intelligence can keep migrating to more durable, more exotic substrates, always staying one step ahead of material decay. But substrate independence, even if it is true in principle, does not escape the thermodynamic constraints. Every substrate must obey Landauer's principle. Every substrate must dissipate energy to compute. Every substrate exists within the causal diamond and is subject to the Bekenstein bound. Changing the material does not change the physics. It does not create new energy. It does not open new horizons. It does not repeal the second law. It is like changing the brand of pen you write with. The ink may be different, but the paper is still finite. And when the paper runs out, the story ends regardless of how fine the pen is. There is one more idea that deserves examination, not because it is likely to work, but because it represents the ultimate expression of the hope that intelligence can survive. The idea of reversible computation. In classical computing, most operations are irreversible. Information is destroyed, bits are erased, and Landauer's tax must be paid. But in the 1970s, physicists Charles Bennett and others showed that computation can, in principle, be performed reversibly. A reversible computer does not erase information. It shuffles it around. Every operation can be undone. No bits are lost, and therefore no entropy is generated. If you could build a perfectly reversible computer, you could compute without paying the Landauer tax. You could think for free. This sounds like the ultimate loophole, but it has a fatal flaw. A perfectly reversible computer cannot discard any intermediate results. Every computation it performs must be stored because erasing any of it would cost energy. This means the computer's memory requirements grow without bound. Every thought it thinks adds to the pile of information it must carry. Over time, the computer needs more and more storage. And storage requires physical substrate. And physical substrate is finite. bounded by the Bekenstein limit and the resources within the causal diamond. So, reversible computation does not eliminate the thermodynamic cost. It converts it from an energy cost to a memory cost. Instead of running out of fuel, you run out of space. The wall is in a different place, but it is still a wall. And in a universe with finite resources and finite volume, you hit it eventually. So let us look honestly at where post-biological intelligence stands. It is better than biology, vastly better. A civilization that transitions from biological brains to optimized machine intelligence gains orders of magnitude in energy efficiency, environmental tolerance, durability, and computational density. It can survive the death of its star. It can function in the cold vacuum of intergalactic space. It can slow its thinking to match the dwindling energy supply and stretch its existence across time scales that dwarf the current age of the cosmos. If biological intelligence is a candle, post-biological intelligence is a fusion reactor. The difference in scale is breathtaking, but a fusion reactor still runs out of fuel. The advantages of machine intelligence are quantitative, not qualitative. They make the numbers bigger. They push the deadline further into the future, but they do not remove the deadline. The constraints we identified, the finite energy, the shrinking horizons, the bounded computation, the non-zero temperature floor, apply to silicon just as they apply to neurons. They apply to quantum processors just as they apply to transistors. They apply to any physical system that processes information in a universe governed by the second law of thermodynamics and dominated by dark energy. The medium does not matter. The physics does. This is perhaps the most sobering realization of all. We tend to think of intelligence as something special, something that, once it emerges, transcends the limitations of the physical world. We tell ourselves stories about minds uploading into computers, about civilizations becoming pure energy, about consciousness escaping the bounds of matter entirely. These stories are comforting. They suggest that intelligence is not just a physical process but something higher, something that can survive the death of its body the way a soul is imagined to survive the death of a person. But physics does not support this narrative. We began this story by establishing that thought costs energy. We have now tested every strategy for reducing that cost or extending the supply: better substrates, colder environments, reversible logic, distributed networks. Each one buys time, none of them buy eternity, because the constraint was never the brain or the chip or the architecture. The constraint is the universe. The thermodynamic walls do not care what you build your mind out of. They close in on silicon exactly as they close in on neurons. The dream of post-biological immortality is not wrong in its ambition. It is wrong in its assumption that changing the hardware can change the ending. The hardware was never the problem. The cosmos was. There is a metaphor that captures this situation with uncomfortable precision. Imagine you are on a ship in the middle of the ocean. The ship is taking on water. Slowly, steadily, irrevocably. You start in a wooden rowboat. The water seeps through the planks. You bail frantically. Then someone offers you an upgrade, a steel-hulled vessel. You accept gratefully. The leaking slows dramatically. You are safer. You are more comfortable. You have more time. But the ocean is still rising. The water is still coming in, not through the hull now, but over the sides, because the ocean itself is rising and there is no shore. You upgrade again to a submarine. Now you are sealed against the water entirely. You can dive beneath the surface and ignore the waves. But the submarine still needs fuel. It still needs air recycling. It still consumes finite resources. And the ocean is infinite. Eventually, the fuel runs out. The air recyclers fail. The submarine, for all its engineering brilliance, sinks. It was never a question of building a better boat. It was always a question of the ocean. The ocean is the universe, the water is entropy, and no vessel, no matter how well built, floats forever on an ocean that has no shore. We have now exhausted every avenue of escape that concerns the medium of intelligence. Biology is too fragile. Machines are more durable but still finite. Reversible computation shifts the cost but does not eliminate it. Substrate independence changes the material but not the physics. Every path leads to the same destination, a finite number of thoughts in a universe that is slowly, inexorably dismantling the conditions that make thought possible. What remains is the synthesis. Everything we have learned, the thermodynamics, the cosmology, the geometry, the engineering, must now be laid out in a single, unflinching panorama. The window of intelligence, how wide it is, how bright it burns, and how, inevitably, it closes. We have now assembled every piece of the argument. We have traced the thermodynamic cost of thought from the glucose in your neurons to the Landauer limit at the edge of theoretical physics. We have watched the stars burn through their fuel and die, one by one, from the great blue giants to the last dim red dwarfs. We have followed the universe past the stelliferous era, through the degenerate era, into the black hole era, and out the other side into the dark era, where nothing remains but a thin, cooling mist of particles drifting through an exponentially expanding void. We have seen the accelerating expansion seal off the cosmos behind event horizons, locking resources away permanently, shrinking the causal diamond to a finite volume with a finite computational capacity. And we have examined the medium of intelligence itself, from the wet fragility of the biological brain to the cold efficiency of optimized machine minds, and found that no substrate, no matter how durable or efficient, escapes the thermodynamic and geometric constraints imposed by the universe. Every path leads to the same conclusion. The total number of thoughts that can ever be thought is finite. The window for intelligence is open now. It will not be open forever. Now we need to look at this window directly. We need to understand its shape, its size, and what it means that we are inside it. Because the most disturbing implication of everything we have discussed is not that intelligence will eventually end. Endings are familiar. Everything in our experience ends. You are born, you live, you die. Stars are born, they burn, they die. This is the rhythm of the cosmos, and we have made our peace with it, or at least we tell ourselves we have. The truly disturbing implication is something different. It is the possibility that intelligence is not just temporary but rare, that the conditions which allow for thinking beings are not a default state of the universe but a brief anomaly, a narrow window of opportunity that opened by accident and will close by necessity, that the overwhelming majority of the universe's lifespan, stretching across timescales so vast they make the current age of the cosmos look like the first syllable of a sentence, will be spent in a state that is not merely uninhabited, but uninhabitable, permanently, structurally, physically incapable of supporting thought in any form. The universe is not a home that intelligence can live in. It is a house that intelligence is passing through, and the doors at both ends open only briefly. Let us map this window onto the actual timeline of the cosmos. The universe is roughly 13.8 billion years old. The stelliferous era, the age of stars, will last for roughly another 100 trillion years. That sounds generous. But remember what comes after. The degenerate era, the long twilight of cooling stellar remnants, stretches for timescales on the order of 10 to the power of 37 to 10 to the power of 40 years. The black hole era, during which the last reservoirs of accessible energy slowly radiate away through Hawking evaporation, extends to perhaps 10 to the power of 100 years. And then the dark era begins, and it does not end. It stretches forward effectively without limit, an eternity of thermodynamic equilibrium. Now compare these numbers. The stelliferous era, the age in which energy gradients are abundant and intelligence can thrive, occupies roughly 10 to the power of 14 years. The dark era occupies at least 10 to the power of 100 years, and likely far more. The ratio between these two numbers is not just large, it is incomprehensible. If you represented the total future timeline of the universe as a line stretching from here to the edge of the observable universe, roughly 46 billion light-years, the stelliferous era would occupy less than a single atom's width at the beginning of that line. Everything after that atom, the entire rest of the line stretching across billions of light-years, would be darkness, silence, equilibrium. This is the scale of the asymmetry. Intelligence exists in a sliver so thin it barely registers on the cosmic timeline. The universe will spend almost the entirety of its existence in a state where no thought is possible, no observer can exist, and nothing happens. This reframing changes the philosophical weight of the problem entirely. We are accustomed to thinking of intelligence as a natural and perhaps inevitable feature of the cosmos. The universe made atoms. Atoms made stars. Stars made heavy elements. Heavy elements made planets. Planets made chemistry. Chemistry made life. Life made brains. Brains made science. It feels like a progression. It feels like the universe is going somewhere, building toward something. We see ourselves as the current peak of a grand trajectory, and we assume the trajectory continues upward. But the thermodynamic timeline tells a different story. It tells us that the era of complexity, the era in which structures can form, energy can flow, and information can be processed, is not the main act. It is the overture. The main act is the long, featureless silence that follows. The universe is not building toward intelligence. Intelligence is a transient side effect of the universe's journey toward equilibrium. We are the sparks thrown off by a fire that is burning down. The fire is the point. We are the accident. This leads to a concept we might call the cognitive horizon. Just as there is a cosmological event horizon beyond which no signal can reach us, there is a cognitive horizon in the future of the universe beyond which no configuration of matter and energy can support information processing. The exact location of this horizon depends on the details: the cosmological constant, the rate of expansion, the efficiency of the last computational systems, the availability of residual energy. But its existence is guaranteed by the physics we have discussed. Somewhere in the far future, the last bit will be flipped, the last logical operation will be performed, and the last thought will be thought. After that moment, the universe will contain matter. It will contain energy. It will contain space and time. But it will not contain minds. It will not contain awareness. It will not contain the capacity to observe, to reflect, to wonder. The lights will go out, and they will never come back on. Now, at this point in the story, there is an almost irresistible urge to reach for an escape hatch. The human mind rebels against finality. We are problem solvers. We look at a locked door and we search for a key. And over the decades, physicists and philosophers have proposed several last resort strategies for evading the cognitive horizon. Each of them deserves examination, not because they are likely to work, but because understanding why they fail completes the argument. The first proposal is Boltzmann brains. We touched on entropy at the beginning of this story, and now its strangest consequence returns. In a universe at thermodynamic equilibrium, quantum fluctuations still occur. Particles still jitter. Energy still fluctuates. And given infinite time, these fluctuations can occasionally produce complex structures purely by chance. A Boltzmann brain is a hypothetical, self-aware entity that assembles spontaneously out of random thermal fluctuations. It appears fully formed, complete with memories and sensory impressions, exists for a brief moment, and then dissolves back into the equilibrium soup. It is the thermodynamic equivalent of a monkey typing Shakespeare. Given infinite time, it happens. So perhaps intelligence does not truly end at the cognitive horizon. Perhaps it simply transitions from organized, sustained intelligence to random, flickering, accidental intelligence. Perhaps the universe will continue to produce moments of awareness, scattered across the eons like fireflies in an infinite dark field. But this is not survival. This is not even a meaningful continuation of intelligence. A Boltzmann brain has no history. Its memories are false, assembled by chance rather than by experience. It has no future. It dissolves almost immediately. It has no connection to any other mind, past or present. It is not thinking in any purposeful sense. It is a random arrangement of particles that happens, for an instant, to mimic the state of a thinking brain. It is a hallucination without a hallucinator, a dream without a dreamer. To call this survival of intelligence is like calling a puddle that momentarily resembles a face a continuation of human portraiture. The pattern is there, but the meaning is not. And the probability of such fluctuations producing anything as complex as a functioning mind is so staggeringly low that the expected wait time between occurrences dwarfs even the black hole evaporation timescale. We are talking about timescales of 10 to the power of 10 to the power of 50 years or more, intervals so long that the number itself is almost meaningless. The cognitive horizon is not softened by Boltzmann brains, it is merely haunted by them. The second proposal is baby universes. Some speculative models of cosmology suggest that it might be possible, under extreme conditions, to nucleate a new universe, a bubble of space-time that branches off from our own and inflates into a separate cosmos with its own physical constants and its own low entropy beginning. If a sufficiently advanced civilization could trigger such a process, it could, in theory, create a fresh universe with a fresh thermodynamic endowment, a new Big Bang, a new stelliferous era, a new window for intelligence. It would be the ultimate act of cosmic engineering, not escaping the heat death, but birthing a successor universe that starts the clock over again. The idea is thrilling, but it faces enormous obstacles. First, we have no confirmed physical mechanism for creating baby universes. The proposals that exist, involving extreme energy densities, topological defects, or quantum tunneling events, are highly speculative and may not be physically realizable. Second, even if a baby universe could be created, there is no known way to transfer information into it. The new universe would branch off and become causally disconnected from its parent. The civilization that created it could not enter it, communicate with it, or benefit from it in any way. It would be like lighting a candle in a sealed room that you can never open. The light exists, but not for you. Third, and most fundamentally, the new universe would face the same thermodynamic trajectory as the old one. It would begin with low entropy, evolve through a stelliferous era, and eventually succumb to its own heat death. Creating baby universes does not solve the problem. It duplicates it. It postpones the question by one cosmic generation, but the question remains the same. Intelligence in the baby universe would eventually face the same cognitive horizon, and no amount of baby universe creation changes the fundamental physics. It is turtles all the way down, and every turtle eventually stops. The third proposal is retreat into simulation. Perhaps a civilization facing the cognitive horizon could build a virtual reality, a simulated universe running on its remaining computational resources, and retreat into it. Inside the simulation, the inhabitants could experience a rich, complex, apparently infinite world, even as the physical universe outside decays into silence. This is a form of the simulation hypothesis turned inward, not asking whether we are already in a simulation, but asking whether building one could save us. The appeal is obvious. If your physical universe is dying, build a digital one and live there instead. But this proposal does not escape the constraints. The simulation runs on physical hardware. The hardware requires energy. The energy is finite. The simulation, no matter how cleverly compressed, no matter how artfully designed, can only run for as long as the computational budget allows. And we have already established that the budget is bounded. The simulation does not create new resources. It simply allocates existing resources differently. It trades breadth for depth, external reality for internal experience. But the total number of experienced moments, the total information processed, cannot exceed the bound set by the Bekenstein limit and the available energy within the causal diamond. Retreating into a simulation is not escaping the prison. It is redecorating the cell. The walls are the same, the sentence is the same, the end is the same. Every escape hatch fails. Not because we lack imagination, not because we lack ambition, but because the constraints are not technological, they are physical. They are woven into the geometry of space-time, the thermodynamics of information, and the cosmological parameters of the universe. There is no trick, there is no shortcut, there is no hidden door. The universe has a finite capacity for thought, and when that capacity is exhausted, intelligence ends. So let us finally sit with this. Let us look at what it means without flinching. The universe may become permanently hostile to observers, not through violence, not through catastrophe, not through malice, through physics, the same physics that built the stars, that forged the carbon in your bones, that sculpted the thermodynamic gradients that power your thoughts, is quietly, patiently, inevitably disassembling the conditions that make those thoughts possible. The cosmos is not turning against intelligence. It was never for intelligence in the first place. Intelligence is a byproduct, a brief, beautiful, astonishing byproduct of a universe that is doing something much simpler and much more fundamental. It is maximizing entropy. It is spreading energy. It is smoothing out gradients. And we, the thinking beings, the observers, the ones who notice and wonder and ask why, exist only because that process is still incomplete. We are the interim. We are the structures that form in the gap between the wound spring and the unwound spring, between the original order and the final disorder. And when the gap closes, when the spring finishes unwinding, the structures vanish. Not because they were flawed, because they were the gap. This is what makes the situation not just sad, but scientifically uncanny. The universe created intelligence, not on purpose, not as a goal, but as an inevitable consequence of the specific initial conditions, the low entropy, the quantum fluctuations, the gravitational instabilities that happen to be present at the start. Given those conditions, given enough time and enough chemistry, thinking beings were statistically likely to emerge. But the same laws that made intelligence possible also ensure that it cannot last. The second law of thermodynamics is both the creator and the executioner. It provides the gradient that powers thought and then erases the gradient. It builds the sandcastle and then sends the tide. The window of intelligence opens because entropy is increasing. The window of intelligence closes because entropy finishes increasing. It is the same process, the same law, the same inexorable, mindless, impersonal physics. And this, finally, is the source of the scientific unease that defines this entire subject. It is not the unease of fear. It is not the dread of an apocalypse or the panic of an imminent threat. The cognitive horizon is so far in the future that no human being, no human civilization, no foreseeable descendant of humanity will ever confront it directly. The unease is deeper than that. It is the unease of understanding that intelligence may not be a permanent feature of reality. That awareness, consciousness, the capacity to observe and reflect and know is not built into the structure of the cosmos. It is a phase, a temporary phase. Like the moment in the cooling of a metal when it passes through a specific crystalline configuration before settling into its final state. The crystal is real. It exists. It has structure and beauty and complexity. But it is not the endpoint. It is a way station. And the endpoint is featureless equilibrium. We live in the crystal right now. We are the crystal. The atoms of the universe have arranged themselves for a brief cosmic moment into configurations capable of self-awareness. We look up at the night sky and we see stars. We look inward and we see thoughts. We look forward and we see possibilities. But the thermodynamic trajectory of the cosmos suggests that this moment is finite. The atoms will rearrange. The configurations will dissolve. The self-awareness will end. Not because something went wrong, because the physics is working exactly as it should. There is a temptation, at this point, to reach for consolation, to say that at least we are here now, that the brevity of the window makes it precious, that the fact we exist at all in this improbable sliver of cosmic time is itself a kind of miracle. And all of that is true. It is emotionally true and it is statistically true. The odds against any particular arrangement of atoms becoming self-aware are so vast that your existence is, by any reasonable measure, an extraordinarily unlikely event. You are a statistical anomaly, a thermodynamic improbability, a brief eddy of order in a river of chaos. And you are here, processing these ideas, right now, in the narrow window when such processing is possible. But the consolation does not change the physics. The window is still closing, the gradients are still flattening, the expansion is still accelerating, the horizons are still shrinking. The computational budget is still being spent, and the vast, silent, featureless future is still waiting. The universe does not owe intelligence a place at the table. It does not owe observers a universe to observe. It created the conditions for awareness once, through a specific set of initial conditions and a specific set of physical laws. And it is methodically, impartially, without intention or awareness of its own, withdrawing those conditions. This is not a story about human extinction. Human extinction is a local event on a single planet around a single star. This is a story about the extinction of the possibility of intelligence anywhere, in any form, at any scale, across the entire observable universe and beyond. It is a story about a cosmos that will spend almost the entirety of its existence without a single observer to notice that it exists. A cosmos in which the era of awareness, from the first primitive nervous system to the last optimized computation, occupies a fraction of the total timeline so small that no metaphor can capture it. A flicker, a heartbeat, a single breath in an infinite silence, and the silence is not waiting for us to fill it. It is not an absence that implies a presence yet to come. It is the natural state. It is the default. Thermodynamic equilibrium is what the universe looks like when nothing special is happening, and for almost all of eternity, nothing special will be happening. We are the special part. We are the exception. We are the brief, improbable, magnificent deviation from the norm. And the norm is silence. Whether that thought terrifies you or humbles you depends on what you expected from the universe. If you expected permanence, if you expected that intelligence was destined to spread across the stars and endure for all of time, then the physics is a cold shock. It is a door slamming shut on a future you took for granted. But if you can adjust your expectations, if you can see the universe not as a stage built for intelligence, but as a vast process in which intelligence is a fleeting participant, then something else comes into focus. Not comfort, exactly, but clarity. The clarity of understanding where you are. You are in the window. You are in the brief, extraordinary, thermodynamically privileged era when the universe supports thought. You are made of matter that was forged in stars that are still shining. You are powered by gradients that have not yet flattened. You are thinking thoughts that are still affordable, in the thermodynamic sense, because the cosmic budget has not yet been spent, and every question you ask, every idea you explore, every connection you make with another mind is an event that can only happen now. Here, in this window, before the window closes and the universe forgets that it ever knew how to think. The stars are still burning, the gradients still exist, the computations are still running, but the meter is ticking. And the universe, patient and indifferent and vast beyond comprehension, is slowly, quietly, inevitably turning out the lights.